Encoder and Decoder LLMs, unlocking the power of language understanding and generation. Introduction. In the rapidly evolving world of natural language processing, or NLP, the rise of large language models, or LLMs, has revolutionized the way one interacts with and understands language. At the heart of these powerful models are the encoder and decoder architectures, each serving a distinct yet complementary role, built upon the transformer architecture. Transformer architecture. The transformer architecture is a fundamental advancement in NLP, enabling the development of highly expressive and versatile language models. This architecture is based on the attention mechanism, which a model can use to selectively focus on relevant parts of the input sequence rather than processing the entire sequence uniformly. This attention mechanism enables the transformer to capture long-range dependencies and effectively process sequential data, such as natural language. Encoder LLMs. Encoder LLMs, such as bidirectional encoder representations from transformers, or BERT, use the transformer's encoder component to excel at language understanding tasks. These models are trained on vast amounts of text data, so they can develop a deep comprehension of language, including its syntax, semantics, and contextual nuances. Encoder LLMs are particularly adept at tasks such as text classification, named entity recognition, and question answering. Key features of encoder LLMs. One of the key features of encoder LLMs is their bidirectional nature, which they use to consider the context of a word or phrase from both the left and right sides. With this bidirectionality, the model can better capture the complex relationships and dependencies within language, leading to more accurate and nuanced understanding. Encoder LLMs also use attention weights, which highlight the relevance of different parts of the input text to the task at hand. To preserve the information about the word order in the input sequence, encoder LLMs use positional encoding. This technique adds positional information to the token embeddings, making sure that the model can understand the relevance of each word's position within the sentence. Encoder LLMs often employ masked language modeling, where the model is tasked with predicting the masked or missing words in the input text. This approach encourages the model to develop a deeper understanding of language structure and semantics because it must infer the missing information based on the surrounding context. Multi-headed self-attention. Another important aspect of the transformer architecture is the use of multi-headed self-attention. In this approach, multiple sets of attention weights, or heads, are learned in parallel, each capturing different aspects of language. This way, the model can develop a more comprehensive understanding of the input with different heads potentially focusing on entities, activities, or other linguistic properties. Decoder LLMs and key features. In contrast, decoder LLMs, such as a generative pre-trained transformers, or GPT, use the transformer's decoder component to focus on language generation. These models are trained to generate coherent and contextually relevant text, making them highly useful for tasks such as text summarization, dialogue systems, and creative writing. The key feature of decoder LLMs is their ability to generate text one token at a time, based on the previous context. With this sequential generation process, decoder LLMs maintain coherence and consistency throughout the output, making sure that the generated text reads naturally and logically. Conclusion. The transformer architecture, often referred to as the encoder-decoder architecture, has been a game-changer in the field of NLP, enabling the development of highly expressive and versatile language models. These hybrid models use the strengths of both encoder and decoder approaches to handle more complex language tasks, such as machine translation, text summarization, and question-answering systems.